The next thing I need to talk to you about is once you've done the programming of the PLC, and when you type in the ladder logic, what you're doing is you're programming the PLC. Once you've taken a relay logic solution, translated it into a ladder logic solution, and you've entered that into a PLC, now you've programmed that PLC. You download the program into the PLC, and by that what I mean is, right, what I mean by that is, you've got a PC. Here's your PC, keyboard, mouse. You've got a PC over there. Here, we've got a PLC, programmable, logical controller. The two are connected. You do the programming inside the PLC using a program like RS Logic 500. You then need to take the program from the PC and send it to the PLC. You download the program from the PC into the PLC. If at any time you want to check to see what's in the PLC and take the PLC program and bring it back to the PC, then you can upload that. So you write the program in the PC, and it looks like a whole bunch of rungs on a ladder, hence the name ladder logic. And you have a whole bunch of switches and a whole bunch of relays. And it looks exactly like relay logic. You enter that program on the PC, and then you download it into the PLC. And then you tell the PLC to run. And the PLC will run, and you're up and running. You should then be at a stage where the PLC is running your program. Now we've got our program should run with a bunch of inputs and 3 outputs. We should have 4 inputs and 3 outputs. We should now have programmed a PLC. Now what we need to do to check this thing is working is we need to wire some switches into this PLC, and we need to wire some little LEDs into the outputs to see if the outputs are coming on. Before we do this, we have to be aware of the possible ways of wiring PLCs. There's 2 ways of wiring inputs and outputs. There's this way. The first way of wiring inputs and outputs is what I like to call the sensible way. The sensible way of wiring inputs and outputs, what we do is, we've got 24 volts. We send 24 volts out to the field where there are switches. When that switch closes, 24 volts appears at the screw on the PLC. When the 24 volts appears on the screw on the PLC, the little LED comes on. The little LED comes on because the other end is connected to the return line. This type of input is called syncing. This is a syncing input. The reason it's called syncing is because the PLC screw, which is marked input 0 or input 1, is attached to the return, which is the sync. So this is a syncing input. Oh, by the way, a quick word. One of the funny things is that the software people like to number from 0. So it's quite common for inputs to be numbered rather than 1, 2, 3, 4. It's quite common for inputs to be numbered 0, 1, 2, 3, 4. It's just one of those little weird software nerdy sort of things that happens. You just got to ignore it really and be aware of it. Right, so this screw here is attached to the return, so it's called syncing. And what we're doing is we're switching 24 volts. On the output side of things, we're also switching 24 volts. We're taking 24 volts in. You know, I really need to put something there. Right, we're taking 24 volts in, and we're switching that 24 volts inside the PLC on a relay contact. That 24 volts then appears on the screw, which is marked output 0 or output 1. That 24 volts goes off to the load, whatever it is that we want to switch on, and switches on that load. The other side of the load is connected to the return line. This is called a sourcing output. The reason it's called sourcing is because the screw on the PLC, which is marked output, is the source of the 24 volts. The screw is the source of the voltage which will run the load, so it's called sourcing. Okay, is everybody with me so far? Right. This is the sensible way of doing wiring. There's another way. The American way of doing wiring. The Americans like to switch return. The Americans also like to switch neutrals, but we won't go into that. American systems, they like to switch the return. It's not necessarily what I'm happy with. So with an American type wiring system, what they have is they have 24 volts on the input screw. The screw here marked input 0 and the screw here marked input 1 has got 24 volts on it. It's connected to the 24 volts. In order to turn that input on, what you do is you short the input down to ground. So you close the switch to put a ground on that input. When you put a ground on that input, the input turns on. It's called a sourcing input. And the reason it's called sourcing is because the screw on the input is the source of the 24 volts. Some of you have already seen how very difficult this is to fault find, and what a totally stupid idea it really is in every respect. It's difficult to fault find because the input is off when there's 24 volts there. When you turn that input to 0, that's when the input comes on, which goes totally against any type of fault finding you might want to do. The second problem we have is that if there is any breakdown, and what's happened with me in the past, I got called into a system where a mobile crane was happily running around all over the plant, and it was an overhead crane, and the reason it was running around was because even though the production manager had pulled the safety key out, the damn thing was still running. What had happened is there was an earth fault. Somebody had cut through the line and connected that down to earth. And the safety key said, yeah, I'm happy now, thank you very much. And so the bloody crane ran. It's really very dangerous. This would not have happened with a syncing input. But, like I say, the Americans like to do that. With outputs, it's actually, if possible, even stupider. With outputs, they like to do the same deal. They like to switch return. which means that the load, whatever it is that we're controlling, has permanently got power on it. So this load, this could be the nuclear warhead, has got power on it. And what we're waiting for is a return to be switched on. And it's called a sinking output because the screw labeled output is a sink. It's a return. Now, of course, here we have a nuclear warhead which has got power on it. If the worst comes to the worst and this accidentally gets connected down to ground, boom. So all you need is somebody to cut through the cable and connect it down to ground, and the damn thing switches on. Lots of equipment coming from the States is wired up this way. Some PLCs use syncing inputs and sourcing outputs. Some PLCs, especially the American ones, use sourcing inputs and syncing outputs. Some PLCs, you can decide. With some PLCs, you can even decide on an input-by-input basis. The problem you get then is, it really depends on who was the last person who did the wiring. The input could be syncing, the input could be sourcing. And when you're doing your fault finding, if you find 24 volts there, if it's a syncing input, 24 volts on an input means it's on. If it's a sourcing input, 24 volts means it's off. It doesn't make fault finding very easy. Some of you may be working for American companies where everything will be wired up with the American standards, which is 24 volt, which is where we switch returns. Some of you aren't. Some of you are working for more sensible companies that wire it up in a sensible way. This is something you have to be aware of. It really is. This is a big trap for young players. That you need to be aware of how the inputs and outputs are switching, whether we're switching the 24 volts or whether we're switching the return, because it makes all the world of difference to your fault finding. And it makes all the world of difference to the kind of faults that you may get on that system. Like I say, if you've got an American system and you've got the nuclear warhead permanently powered up, all you need is somebody to cut a wire, that wire to short down to ground, and boom. Okay, everybody ready to move on? With the Alan Bradley, the translation table I've given you, as far as this course is concerned, as far as the course that we've designed is concerned, we are not teaching Alan Bradley. We are teaching generic PLC programming, so that you can take this programming that we teach you to a Yokogawa or a Honeywell. You don't have to just use this on Alan Bradley's. But sometimes people want to know exactly what it is that they're typing in. So just in case you want to know what these funny numbers are that we tell you to use, it works this way. The first letter tells you the type, and it's going to be something like I for input and O for output. So we have the first letter is I equals input, O equals output. Or it could be B3, which means internal relay. Yeah, I don't know, Mr. Bradley must have thought that was a good idea. The second letter tells you the slot number. With the Alan Bradley, what we have is we have a main PLC, and then we have other modules attached. So that if you go out through this module here, that would be module number 2. That would be module 1, that would be module 2, and the main PLC counts as module 0. And then we have word and bit. Now, word and bit I'm going to be explaining in the next lesson. This does bring up a very interesting point. When you're doing programming in PLCs, and it doesn't matter whose PLCs you're programming in, the main problem you're going to get is that you type something in incorrectly. The main problem you're going to get is with the fact that I equals input and O equals output. The problem you're going to get with that is that 1 equals on and 0 equals off. And it is very, very easy to make the mistake of typing in a 1 when you meant to type in an I. And it's very, very easy to type in a 0 when you meant to type in an O. So the main problems you're going to get is that you've entered the wrong thing, and it's going to come back and say syntax error, or input doesn't exist, or some other really useless alarm it's going to come up with. And the problem is going to be 99.9% of the time, the problem is going to be that you've typed in a 1 instead of an I, or an I instead of a 1, or a 0 instead of an O, and an O instead of a 0. It's just really unfortunate that the two letters we use in English language are input, which is I, and output, which is O. And I and O look so like the two numbers that we use, which are 1 and 0. It's just a shame, really. Now, going back to our gunnery computer. We're round about the 1950s, 1960s. The American Navy is still every bit as bad at hitting the bad guys as it ever was. They still need computers to help their gunnery. We've always had gunnery computers in battleships, and it's always been the gunnery computer that really won the battle. Right the way back from the Russian-Japanese War of 1870. It was always the gunnery computers that decided what was won. Definitely in the First World War, the Battle of the Battle of Jutland was won, well, was a draw. But the Germans did a lot better than the British at that battle because they had much better gunnery computers. They've always had these computers. And these gunnery computers would do things. You would have they would work on hydraulics. And you would dial in one pressure, which would correspond to the ship's speed. You'd dial in the second pressure, which would correspond to the ship's course. You dial in a third pressure to correspond to the other ship's speed, and a fourth pressure which corresponded to the other ship's course, and you dialed in another pressure which corresponded to the wind direction, and yet another pressure for the wind speed. And all of these pressures would go in, and what would happen is they would traverse the guns. So they would spin the guns round to the correct course, and they would elevate the guns to the correct height. And then when the gunnery computer was just all happy that the guns are in the right place, you'd fire the guns. If you had a really good gunnery computer, you might even hit the bad guys. Chances were you didn't. So they really needed to work on these gunnery computers to improve them. So the American Navy commissioned some people to write some programs for them to improve their gunnery. Now, at this point, something absolutely amazing happened. The Americans had a good idea. Somebody said, look, okay, I'll write you a computer program, but what do you want the computer to be? Do you want to continue using your hydraulic gunnery computers? Or would you like to use pneumatic gunnery computers? Or would you like to use mechanical computers like Babbage built with the levers and pulleys? Or would you prefer to use electronic computers? We've got electronics nowadays. 1950s, they had valves and all sorts of tubes and all sorts of fun stuff. Or would you even like to use one of these newfangled digital computers? What would you like to use as a computer? And at this point, somebody had a good idea. And they said, really, what I want you to do is I want you to write a program that will work on all of them. So the person went off and they created a programming language, a programming system. And that programming system was called Block, Basic Language of Control. It's often called function block programming. And block programming relied on a couple of things. The first thing block programming relied on was that it would be independent of the platform. It wouldn't matter if you were running it on a digital computer or a hydraulic computer or what have you, it would still work. Block programming would hide from you how it worked. All that you have with block programming is little boxes. So you pull a little box onto the screen and you have a little box, and that little box does a job. So if you want to do an exclusive OR, you have a box called XOR, and it has a couple of inputs and it has an output. And the whole main thing about block programming is you don't know how it works. The only thing you know is that you have two inputs labeled A, B, and you have an output which is labeled, well, say it's O, and it works like this. When A and B are off, that's off. When B is on, that's on. When A is on, that's on. But when both of them are on, it's off. So you don't know how it works, you just know that it does work. That's function block programming. The workings are hidden from the programmer. And because the workings are hidden from the programmer, it could be hydraulic, could use the hydraulic switches, or pneumatic, or electronics, or digital. The program doesn't change. Just the thing that it sits on, the platform, changes. To program in function block, it's simply a case of you have a white screen on the computer and you pull the blocks in. Now, those of you that have got the resource pack from us, in there's a simulator for the Cruzette PLC, which uses function blocks, and you can run that up and simulate function block programming. So there's also an exercise in the book, let me just see if I can find it, exercise 3 on function block programming. So you can have a little go at doing the 3-pump problem, but using function blocks. Using function blocks and pure logic, the 3-pump problem looks like that, which doesn't look too great. But there are easier ways of doing it. This is a true function block solution to the 3-pump problem. And you can see it's a graphical representation. It's on the exercise on page 311 or 312. And so you can see this is a truly graphical representation. This is the program as it looks. And to program this, you drag the appropriate blocks on. To connect things together in function block, what you do is you drag a... Oh, let me grab a square. You drag a block in. Let me do that again. Right. What you do is you get a block, you drag it in. Say this is an XOR. It's got a couple of things there and a thing there. Outputs are just boxes that live on the right. The rule we always have with PLCs is in on the left, out on the right. So we've got a couple of ins and an out. We've got an XOR. with function block programming, the workings are hidden from you. So you have an input which is called input 1, you have an input which is called input 2. You don't know whether that's a hydraulic input or pneumatic input, and you're not allowed to know because it's function block where the workings are hidden. To do the actual programming, all you do is draw lines from the inputs to the thing you want it to do. And in the output from the exclusive OR, you draw a line to the output. And that's it, programmed. So the output 1 over here, that's output 1. Output 1 now comes on when there's an exclusive OR function between input 1 and this is input 3. That's all you do for function block programming.